In this video, we are going to talk about how we can test if a series diverges using the nth term test. So the nth term test, which is sometimes called the divergence test, says that if we have some series, if the limit of the terms is not zero, then the whole series is going to diverge. Okay, so conceptually what that means is if you look at these terms and eventually you keep adding some number, like let's say the limit is 2, and I keep adding 2 and then something very close to 2 and something very close to 2, well, eventually that's going to be infinitely large. So I would expect the whole thing to diverge. So I can express this in an equivalent way using what's called a contrapositive. The contrapositive takes an if-then statement. It switches the order of the if and the then, so they switch spots. And then you say the opposite of both of them. So what that would be is if this thing doesn't happen, meaning if the series actually does converge, then this one's not going to happen, meaning the limit of the terms would actually be 0. And I think conceptually that makes sense. Like if the series were to converge, the only way that can happen is if the limit of the terms was 0. Because if the limit wasn't 0, it would have diverged. I can also think about the contrapositive visually by drawing a circle for the first statement A and a circle for the second statement B. And this would be saying, well, if A happens, then B happens. Like if I'm in the A circle, well, then I'm definitely within the B circle. I can also write the contrapositive of this. So the contrapositive says, okay, if B does not happen, which I'll say if not B, then not A, then A doesn't happen. So why is that? Not B means if I'm not in the B circle, I'm out here. If B doesn't happen, I'm out there. But if I'm out there, I'm definitely not in the A circle. A is definitely not happening. And that's the logic of the contrapositive. All right, so let's do some examples. So does this series converge or diverge? Well, let's first play around with it. Let's plug in some values. So if I plug in 1, I'll get 1 over 2. If I plug in 2, I get 2 over 3. If I plug in 3, I get 3 over 4. And I could keep going like this. So I get plus dot, dot, dot. I want to have you at this point try to find the limit of this and then see if you can use this divergence test to determine what ends up happening with it. So give the video a quick pause for 1 minute to try that. In 3, 2, 1, pause it and try it. Okay, so hopefully you did that. Hopefully you paused it to try it. So let's talk about it. So if I wanted to do the limit of the formula for the terms, if I try plugging in infinity, I get infinity over infinity. Oh, that's something I can do L'Hopital's on. So I put my equal sign. I write LH to indicate I'm doing L'Hopital's. And then I get my limit as n goes to infinity. Derivative of the top is 1. Derivative of the bottom is 1. Oh, and 1 over 1, that's just 1. There's nothing to plug an infinity into. That means this limit ends up just being 1. In fact, you might have noticed that these terms, eventually you get further and further out, they're just getting closer and closer to 1. So because this limit, the thing I care about is, well, it's not 0. Based on this divergence test, this nth term test, the series diverges. The series diverges. The conceptual reason for that is as I get further and further out, I'm adding something that's really, really close to 1, and then again, something that's really, really close to 1, and then again, something that's really, really close to 1. It's not exactly 1, but really close to 1. Like this might be like 0.999, and again, something that's like 0.999, like really, really close to it. And if you add enough of those, it'll make the whole thing be infinite. It'll diverge. So now a cautionary warning, which is, well, what happens if the limit of the terms is actually 0? It might be tempting to say, well, then doesn't the series just converge? But it turns out, oh, not so fast. The series might converge, but it also might not. I want to look at some examples to see why that is. But I first want to mention, like, wait, doesn't this seem to contradict what we said here? But not exactly. There's a difference in the order in which these are stated. The contrapositive here says, hey, if I know the series converges, the only way that can happen is then if the terms, their limit is 0. But this is switching it. It's saying, hey, if I know the limit of the terms is 0, then does the series converge? It turns out maybe, maybe not. So let's look at these examples. So does this series converge or diverge? So let's write out some of the terms. If If I plug in 0, I get 1. If I plug in 1, I get 1/2. If I plug in 2, I get 1/4. Plus dot dot dot, I get 1/8, and so on. We've actually seen this series a couple of times in this section. This is geometric. It is geometric. And so the key thing I need to know what's R, the common ratio here, that I keep multiplying one term by to get the next, is 1/2. In fact, I can see that from the formula. I got my R to the n power. It's 1/2. So the key thing I look at in a geometric series as well is the absolute value of R less than 1. And yeah, here it is less than 1. And when that happens, it converges. We could even figure out the sum of this if we wanted to. We've actually done that in 3 different ways earlier in the section, so I won't do it again. But yeah, this is an example where it converges. And if I were to look at the limit of these terms, if I were to look at the limit, just to verify, hey, the limit as n approaches infinity of my 1/2 to the n, well, this means 1/2 to the infinity power. That's 1/2 times 1/2 times 1/2 times 1/2 forever. That's just getting close to 0. So the limit of the terms does equal 0, and in this case, the series ended up converging. Now we're going to end by looking at an example where I have this series, and if I plug into this, I'll get 1 plus 1/2 plus 1/3 plus 1/4, and so on. So the terms do seem to get closer and closer to 0. Like if I plug in infinity for this, I'll get 1 over infinity, which is 0. The terms do get closer to 0. But it turns out it's going to diverge. So this is a classic example. It's something called the harmonic series. So why does this diverge? So here's how we can argue this. I'm going to group the terms together. I'm going to put the first one by itself and the second one by itself. Then the next 2 I'll put together. And then I'll put the next 4 together. And then the next 8, and then so on. And now the first 2 groups are like simple enough. I'll leave them as it is. But now with the next group, what I'm going to notice is if I were to replace the 1/3 by just a 1/4 and keep the other 1/4 as it is, this new sum is less than this original one. So I'll put this inequality symbol here. This thing is greater than this one because 1/4 is less than that 1/3. I'm going to do the same thing over here. I'm going to replace the 1/5 with 1/8, which is smaller, and 1/6 with 1/8, and 1/7 with 1/8. And keep that last 1/8 as it is. This new sum is smaller than this original one because I've made 3 of these fractions now be smaller. And I would keep doing the same thing with all of these subsequent groups. So what does this now give me? Well, I have that 1, and then I got that 1/2, and then plus I got 1/4 plus 1/4, which, ooh, that's 1/2. Plus, and then I got 4 of these 1/8s added together, and shocker, that's also 1/2. And if I kept going like this, this next group, the same thing with it, that would also give me a 1/2. I keep getting 1/2 plus 1/2 plus 1/2. So this sum here, this is definitely infinite. So what has that shown? This original series I was looking at, that's bigger than this new thing, which is infinity. So what that means is this original harmonic series, it's greater than this series, which I know is infinitely large. That means the harmonic series is also infinitely large, if it's even bigger. So it diverges. So even though the limit as n approaches infinity of just this formula for the terms of just the 1/n, that ends up being 0. That's not enough to say the series converges. It actually diverged here. So the moral is, if the limit of the terms, if I check it and it's 0, it could converge like it did here. It could diverge. It depends on the series. So in and of itself, this doesn't tell me any info unless I do more analysis. So to end, let's recap our strategies for checking if a series converges or diverges. So a common thing I might try first is I might try the nth term test if I wasn't sure what to do. If that limit of the terms is not 0, it diverges right away. If the limit of the terms is 0, maybe it converges, maybe not. So I would ask myself, what is it a series that I know? Like, is it geometric or telescoping or harmonic? Like this one was geometric, so I could use that to figure out if it converged or not. So if it's one of the ones I know, use the methods that I have for that type of series to figure out if it converges or not. If it's not one of the series that I know, there are ways of handling it. It's typically taught in Math 23 at Santa Clara. It involves doing things called a series convergence tests, which are just they're beyond the scope of our class. So we don't need to worry about them for our class.